So in this video, we're going to be talking about how quantifiers interact with negations. And there are a couple of fundamental things to get through. First of all, the following two things are logically equivalent. It is not the case that for any x, p of x is true, is the same thing as there is something for which p of x is false. Okay? Intuitively, what we're saying is, if this statement is not always true, then sometimes it must have been false. Similarly, if a statement is sometimes false, well then it was not always true. That's the intuition behind it, okay? Now, a lot of students will nod their heads and say, yes, yes, that makes a perfect amount of sense, but then what they'll do is they'll go through a problem and they'll just say, the negation of something always being true is just going to be followed by, for any x, it's false. These are not the same thing. Just because a statement isn't always true doesn't mean it's always false. Okay, so the intuition is if it's not always true, it is sometimes false, and if it is sometimes false, then it is not always true. Also, if a statement is not ever true, then it was always false. If there is not anything for which p of x is true, then for anything p of x is false. And in the reverse, okay, if there is nothing, or sorry, if for anything p of x is false, then there is not anything for which p of x is true. In other words, if you negate a universal quantifier, you end up with an existentially quantified negation. If you negate an existentially quantified statement, you end up with a universally quantified negation, and vice versa. Okay, but in order to prove this, what we have to do is we have to establish four different statements. Namely, to establish both of these logical equivalences, we need to show, okay, that this right-hand side implies this left-hand side. Then we need to show that this right-hand side implies this left-hand side, that this left implies this right, and that this left implies that right. Now, in theory, any order you prove these four statements in, these are the four things you have to show, and then you will have established both of these logical equivalences. So here's what they represent. If there is something for which p of x is false, that's the hypothesis of line 1 here, then it is not the case that p is always true. Line 2 says, if for any x, p of x is false, then it is not the case that there is something for which p of x is true. If it's not the case that p is always true, then there must exist a thing for which p is false. If it's not the case that there is a thing for which p is true, then for anything, p must be false. And now what we're going to do is one by one, all four of these things we're going to prove as two-column proof. Let's get right to it. Here was the first thing that we needed to prove. There is a thing for which p of x is false, therefore it's not the case that for everything p is true. Well, we begin by making our given, that's line 1, and then we assert our desired conclusion. This was not a conditional statement, so we assume its exact negation. Now we can instantiate the assumption that has to do with p of x being true and our given that has to do with p of x being false. Since I'm going to instantiate an existential and a universal, I do the existential first, and I instantiate them with the same variable. Okay, because I want them to be instantiated with the same variable, I needed to do the existential one first. Why was it important to instantiate both of these with the same variable? Because now we have a contradiction, p of a and not p of a. Now that we have generated a contradiction from this assumption, the assertion is proved and we're good to go. Okay, so for the moment, we're going to call this the first rule of negating quantifiers. Remember, we needed four separate things. We're proving them in a particular order because having some of them proved is going to be useful as steps in proving the later ones. So this is right now just called the first rule. So let's go ahead and try to prove the second rule. Well, we've got a given, we make an assertion, we assume its negation. Okay. I've got a universally quantified thing about p being false and an existentially quantified thing about p being true. So I'm going to instantiate both of them, and I do the existential one first, and I use the same variable for both so that I can generate a contradiction justifying that assertion. And for now, we're going to call this the second rule of negating quantifiers. Okay, so there were 4 things to prove. We've proved the first, we've proved the second. So let's take a look at the third. Okay, it is not true that P is always true. Therefore, there must be something for which P is false. So we start off with our given. Okay, now what I don't necessarily want to do is just assert this, because if I asserted this, it's not a conditional statement. I could just do an indirect proof. I would assume its negation, and we haven't actually proven anything about handling negations of existential statements. So what we're going to do, and this is a little tricky, okay, in line 1, I'm simply replacing P of x with the logically equivalent not P of x. The second rule, however, inside this parenthesis said, if you have a universally quantified negation, and the statement that we are now saying we're negating is not P of x, if you have a universally quantified negation, that implies a negated existential of the same statement. So that was our second rule. And now I can apply double negation here. So we have moved from, it's not the case that for any x, P of x is true. Therefore, there exists something for which P of x is false. And we're going to call this the third rule, which only leaves this fourth one. So we've got a given, we make an assertion, we're going to assume its negation. The third rule told us if you don't have for all x something, then there exists an x for which you have the negation. And we're doing a hidden use of double negation here. You would pass this negation inside, and then you would say not P of x is the same thing as P of x. But now notice that we can conjoin the line we just extracted, there is a thing for which P is true, and our given, there does not exist a thing for which P is true. What I cannot actually do is instantiate both of them with the same variable to get a contradiction. For 2 reasons, okay? 2 different existential instantiations with the same variable would be bad. Also, this isn't really an existential statement, it's a negation of an existential statement. So you'd have to do something else there. Remember, when you do instantiation, the quantifier has to be the leftmost thing that you're taking care of. But still, we've conjoined 2 things, a statement and its exact negation. So we have generated a contradiction and backed up the assertion. And now that we have established all 4 of these rules, we're just going to condense them into the following equivalences. As stated at the beginning, okay, the negation of a universally quantified statement is equivalent to an existential quantifier on the negation, or the negation of an existentially quantified statement is equivalent to a universally quantified negation. These are intuitively fairly straightforward, and thankfully, we were actually able to prove them. Okay, any of these equivalences can now be used in a 2-column proof under the name negating a quantifier or a negated quantifier. Jumping right into it, we're going to generate 2-column proofs. So here we go. Okay, we go ahead and make our givens. Then we're going to assert our desired conclusion. It's not a conditional statement, so assume its negation. Now we can use the new rules of inference we just discussed. We have a negated existentially quantified statement, which is logically equivalent to a universally quantified negation. It's not the case that there is a t for which this is true. Therefore, for any t, it must have been false. And this is one of the new logical equivalences we just did, called negating quantifiers, applied to line 3.1. So now look, we've got for any t, we don't have r of tx. There exists a thing for which r of x, comma b. So we're going to go ahead and say, existentially instantiate and universally instantiate those 2 lines. The existential instantiation needs to come first because I want to use the same variable in both. I want to replace b with z in line 2 so that I get r of xz. And I want to replace t with z in line 3.2 so I get not r of zx. So what we've generated is r of xz and not r of zx. Now these do not immediately contradict one another. The fact that x is on the left and z is on the right versus z is on the left and x is on the right means these are different statements. So if I were to conjoin these two things, I would not yet have a contradiction. But we haven't used line 1. Line 1 says if you have r of two things, you can always extract, always, r of the same two things in the opposite order. So I could apply line 3.3 and universal modus ponens. We could also do universal modus tollens if you wanted to use line 3.4, but whatever. If I feed in r of xz, I extract out r of zx, and that's what we get here. And now I have two things that are exactly the opposite. Conjoin those two things, now you have a contradiction. Now that we have a contradiction from our original assumption, the indirect proof is completed, which finishes off the entire proof. Another example. So this begins like so many other. Okay, we list out all of our givens, we assert our desired conclusion, and then we make an assumption depending on what form we're going with. Since we asserted something that's not a conditional statement, we're going to go ahead and do an indirect proof. Well, we're going to use our new rule about negating quantifiers. A negated universal quantifier becomes an existentially quantified negation. So now we just have to ask, how does this new information interact with our given? Well, if I existentially instantiate line 2 with the variable t, then I universally instantiate line 1 with the variable t twice, okay? As we discussed, two consecutive universal instantiations can be done in one line. I just want to be very clear about it here, so I'm doing it as two separate lines. Okay. But we're just throwing around t's everywhere. Since we're going to be reusing the same variable, the existential instantiation has to come first. But now what do we have? We have not p of t or p of t. This is a little weird to state, but I'm just going to do a resolution between these two lines. If I have the negation of one of the arguments, then I extract the other. So if I resolve negation p of t with p of t or p of t, since I don't have one argument, I must have had the other one. There's another way you can get from this line to this line. There's a logical equivalence that, depending on which exercises you've been assigned, back in propositional logic, you might have established that p or p is equivalent to p. I forget the name of this logical equivalence. It's not very commonly used, but if you had that, then you would have statement or statement is equivalent to statement. That's another way you could get from line 2.5 to line 2.6. But however you do it, now you have p of t, you have not p of t, conjoin them, and you've got a contradiction. Now that you have a contradiction, the assertion is justified and the proof is complete.